So now that you've seen how to use parallel streams to some extent, now that you've seen sort of how parallel streams is implemented in terms of the piece parts, let's kind of put it all together, and I'll show you how a parallel stream is actually constructed and executed. So I've shown you the bits and pieces, but I haven't really shown you what it's doing kind of holistically under the hood. So if you recall, I mentioned before that intermediate operations in a stream are lazy, right? They don't actually do anything until the terminal operation is called. So when the terminal operation is reached, then the intermediate operations start to run. Well, what the heck does that actually mean? And so the way this works under the hood is when the Java code, the Java compiler will compile this code into something, and when it runs the bytecode or the ahead of time compiled code, whatever, when it runs the code that does this, it doesn't actually start to execute these methods when they're encountered in the binary version of stuff or the bytecode version of stuff. Instead, what these methods do, these intermediate operations, is they actually create a linked list at runtime that contains the stream source, like an input list, and the intermediate operations. So you have a linked list that puts all these things together, and there's one stage, or there's one node in the linked list for every stage in the pipeline of intermediate operations. So internally, there's a data structure that's used to represent each of these different kinds of intermediate operations, and it simply makes a linked list of these things. So that's kind of cool, and you can read more about that here at this link. Each of the stages in the pipeline is described by the linked list node using a bitmap of stream flags. So the internal representation has flags that go along with other internal data that's stored as part of the stream. And here's some of the things that are put into this bitmap of stream flags. It indicates whether this operation is sized, distinct, sorted, and ordered. And so sized means we know how big the stream is. Like, let's say you have a stream of n elements from an array list. We know ahead of time how big that is, right? There's n of them. Are the elements distinct? Well, that would be the case if we had a collection that was the source of the stream that was known to be distinct, like a set, for example. Conversely, something like a list, we don't know if that's distinct, so it wouldn't be considered distinct. That flag would not be set. Are the elements in the stream sorted in some kind of order? That would be the case if we had, for example, a tree set. But of course, if we had a hash map, we couldn't set that flag. And then the other field here, which is a little confusing because it sounds like sorted, but it's actually different, is ordered. Does the stream have a meaningful encounter order? So again, a list has ordering properties, whereas a hash map does not. What's interesting about this is these flags are a subset of the flags that can be defined by a split iterator. So if you go and look at the source code for the various collections in Java, you will find that there are split iterators for each of these things, and those split iterators set flags that describe metadata about the split iterator that's created for the collection. It indicates properties about the collection, whether it's size, distinct, sorted, and ordered. And so that information is known up here, and then it can be sort of propagated through the stream as you go down. Okay, so that's one thing to remember. Now, at each of the stages, the flags for a given stage are derived from the split iterator characteristics. So, for example, an array list is sized and ordered, but not sorted or distinct. Now, of course, it might happen to be ordered, or might happen to be sorted, but that doesn't matter from the point of view of the way that streams works. It just knows that it is sized and ordered. A hash set is sized and distinct, because there's no duplicates in a hash set, but it may or may not be ordered, and counter order doesn't necessarily matter, and it may or may not be sorted, because it will be a hash set. A tree set, in contrast, is sized, ordered, sorted, and distinct. So it's got all the little check marks flagged. Interestingly enough, some of the stream factory methods like generate and iterate will create non-sized streams. They could potentially be infinite in their duration, in their size, because they're just going to keep generating until you say uncle, or until you say limit, or something like that, or until your program runs out of memory. All right. So that's what happens when things start, right? So each collection starts out with these properties. Each intermediate operation then affects the stream flags. So for example, if the map function is called, if the map aggregate operation or intermediate operation is called, it will do certain things to the flags. For example, it'll keep sized set, because remember, map can't change the number of elements, but it'll clear sorted and distinct, because map could make changes, right? Map could change every value to 0. So, or just change it. It could change it in such a way that it's no longer sorted and no longer distinct. So it'll change those properties. Filter clears sized, because you could have fewer items, but it keeps sorted and distinct set. And sorted keeps size and distinct and adds sorted. So the sorted operation will change the flags. As the pipeline is being constructed, the flags at each of the stages will be updated. This is all done magically for you underneath the hood, so you don't have to worry about how it works. So flags for a previous stage are combined with the current stage's behavior to derive a new set of flags for that new stage. Here's an interesting example of how this information can be used to optimize system behavior. So let's assume that we were going to make ourselves a tree set. So we have a set that's a tree set, not a hash set, but a tree set. So that means the sorted flag will be set. When we turn this into a stream, that will preserve the sorted flag, because that's what the splitterator will know. And then when we get down here, if we have a sorted operation, then we know that that's redundant, because we started out with something sorted, and we haven't done anything to unsort it. We haven't done a map call, for example. We've only done filter. And so as a result, it knows it can ignore this and eliminate it altogether. So that's an example of how streams can be smart about how it works by optimizing the behavior of the system in some way. All right, so then the question comes, how does all this stuff actually happen to run? I told you kind of how it builds up the internal data structure that's a linked list of source and intermediate stages. When the terminal operation is encountered in the linked list, then the stream framework says, okay, now I've actually got to do something. I've got to start to run. And what it does is it picks an execution plan and runs everything. And this execution plan is actually quite interesting. So the plan that's used to decide how to run the stream is based on the properties of the source, like is it sorted, is it distinct, is it ordered, and the various aggregate operations that it happens to find throughout the stream. Intermediate operations, these guys, are divided up into two categories: stateless and stateful. Stateless aggregate intermediate operations include things like filter, map, flat map, and so on, where the stream doesn't really have to know anything about what came before in order to figure out what to do next. And if you have a stream pipeline that only has stateless intermediate operations, then the whole pipeline can be processed in a single pass, even if you have parallel processing. Because all you'll do, remember how things work in a stream? Remember how the next element from the data source is pulled through all of the modules in the linked list, all the stages in the linked list, applying the operations from beginning to end. That's called intermediate. That's called layer. I always forget this. It's basically an optimization for collapsing layers. And so if you have only stateless operations, then the whole thing is done in one pass. And if you have a parallel stream, then each thread in the fork join pool will do it in one pass. Conversely, if you have stateful operations, then those operations have a different behavior. And stateful operations are ones where for the intermediate operation to do its thing, it has to know what's come before. So in the case of sorted, like if it's sorted, it's got to get all the results of the previous layers so they can sort them, right? If it's distinct, it has to get everything from before to get rid of duplicates. If it's limit, it has to get the, it has to know how many things have happened so far so it can limit it to a certain amount. And a pipeline with stateful operations is divided up into sections and runs in multiple passes. So what will happen is everything that's in the stateless portion will be run first. The results will then be buffered, and then the next stateful operation will run on the results of the buffering, and then that'll be taken out and passed to the next stage, and so on. And if you have stateless operations, then that can run until you hit another stateful operation or you hit the end. Yes?
So if there's, let's say there was a stateful, get that.
Exactly, that's right. So the bottom line is stateful operations, I mean, if you need them semantically, you need them semantically. If you need something sorted, you need them sorted in order to do the next phase. But they do incur a cost. Terminal operations are also divided into two categories. So we have two categories of intermediate operations, stateless and stateful. Terminal operations also have two categories, non-short-circuiting and short-circuiting. So non-short-circuiting operations are ones that basically just do everything up to the point where an exception is thrown or you're finished. And that would include all the things we've talked about so far, reduce, collect, for each. And these can be optimized so that when you get to doing the collect portion or the reduce portion, you can use, if you have non-short-circuiting operations, you can do these things with the for each remaining bulk iterator operation. So for each remaining, we'll simply go through everything and apply some action to it. Conversely, short-circuiting operations can stop when a condition is satisfied. So a good example would be, find me the first thing, or match anything, right? These are like basically short-circuiting. I don't tend to use these a whole lot, but they do exist, and so you should be aware of them. So find first, match any match, and so on. And in that case, because we don't know if we're going to keep going, we have to, the streams framework has to process those with try advance. So it'll do it one at a time, as opposed to doing them in bulk. So obviously, again, that's going to be a little bit slower. Oh, by the way, I finally remembered what the term was. Integrated layer processing. That's the idea of doing all of the layers in one thread of control rather than doing everything at one layer first, then doing everything at the next layer second, then doing everything in the third layer next. So if you have stateless operations, integrated layer processing can be used to optimize things, and it typically runs a lot faster. Okay, so that's kind of the overview of how streams work under the hood. Hopefully that gives you a little bit better perspective of what it's doing. And the good news is that you don't really have to know or care about these details. It's just there so you're a little smarter about how it works. And in particular, when it comes to parallel streams, it's important to know how these things work because that'll affect your choice of operations. In particular, parallel streams, to make parallel streams work fastest, you should try to stay away from stateful operations, and you should try to stay away from short-circuiting operations, if you can. I mean, obviously, if you need them, but your parallel streams will run a lot faster if it's stateless because then everything can truly run in parallel with no dependencies on having to wait at some end of some phase for all the other processing to finish before you continue on with the next item in the pipeline, the next intermediate operation in the pipeline. So it's just a kind of good thing to remember if you have a lot of short-circuiting, if you have a lot of stateful operations, your parallelism may not work the way that you expect it to work.